Hello, guys. Welcome to another episode of CUDA Education. This video is very short and to the point. All I want to do is connect the dots between what happens on CPU side and what happens on GPU side as it relates to um, transferring the attached to cursor feature in our example. So this is a sort of a part two of the first attached to feature episode. So this is part 3.1 in the compute particles series. But so for those of you that don't know and you don't want to look at the first video, basically we have an application here where there's a bunch of particles and there's this natural thing that happens, and then if you do attach to cursor, then we sort of get this initial repulsion, but then eventually the particles move towards the cursor. So it's an initial repulsion, but then it moves towards the cursor. And we could see that because if we run it again, I do attach to cursor and I just leave the mouse in the middle, you're eventually going to see that everything eventually makes its way back towards the cursor. And that is as a result of the logic that we have in the background. Now, the thing is that, so if I run it again now and I don't do a attach to cursor feature, and I just have my mouse here, you'll see that the natural progression of the algorithm is a lot different. So eventually they bounce off the sidewall of the monitor, or the window, but it isn't the same necessarily attraction as we had when I turned on the attach to cursor feature, right? So that's all this is. I'm not going to go through the whole thing of this algorithm because I sort of already did that with the compute n body examples. So the compute n body, if you search my channel, you'll see that I have a whole series on compute n body, and actually this example is a lot simpler than that example. So if you follow that example, you would basically, have a means of understanding how this algorithm works. Again, the particles run independently of each other. There is no gravitational pull that or awareness of the other particles that are around any given particle. So you don't have to do like two compute passes and all of that, and sort of figure out how many other particles are around you. Everything just runs independent of each other based on a mathematical equation, all of that good stuff. So the purpose of this video is, what I wanted to do is just to connect the dots between where is it? I just want to connect the dots between the the cursor information and the delta and all that on the CPU side to what's going on the GPU side, right? So we have this logic right here, layout binding to UBO, and we have delta T, which is sort of a clock dealing with the CPU side clock, the you know dest X, dest Y, which deals with where is the mouse X and Y, particle count, all that stuff, and it's being moved to the UBO. Right now, all this stuff, we've done this a million times, but I just wanted to clear this small part up just to be done with it and and we could move on to compute ray tracing. Okay, so um, we have this logic here where it's binding to, and we're doing descriptor sets, compute descriptor set, uniform. The type is descriptor type uniform buffer, and basically the binding number is number 2, and we're passing in compute uniform buffers, right? So this compute uniform buffers is what is compute uniform buffers, right? So this compute this statement, this function is in the prepare compute function. Okay, so create a compute capable device, what have you. Create compute pipeline. Compute pipelines are created separate from graphics pipelines, even if they use the same queue, family index. We need the previous particle positions to calculate data for the current frame. Okay, so long story short, that is that. But what I wanted to, what I wanted to show is that, for example, if I, is it, I believe it's this one, right? If I retard the binding that this is being connected to. So if I instead of this being 2 and I make it 3, basically what's going to happen is that now I've disconnected basically everything, right? Including the cursor attraction, all that stuff, right? No calculations are happening because um, the UBO is expecting binding 2 and I have binding 3 here. And literally that's what I wanted to show in this video, right? Nothing special. If I change it back to 2, then we get back our functionality where we get our delta t, dest x, dest y, particle count, all that stuff, right? So if I change it back to 2, I will get back the connection to the, everything will sync up properly and we get back our application as we had before. And that's pretty much it. But just know that this is CPU side, this is GPU side, and when you get into definition, go to definition for we have destination set type, and then this is our binding. So this is the guy that is this guy right here, that is this guy right here. Okay, and there's a lot to go into this, but if you go through the compute n body example, you would more than be able to process what's going on in this example. A lot of code as always. This is Vulkan after all. But I just wanted to make that connection, and really and truly the reason was it was this mouse state. So see, we have dest x is normalized, we assign dest x and dest y here, and that is what's being copied here. Okay. Um, so this is the actual copying of the data to the GPU into the uniform buffer memory, right? So the actual bytes of uniform data into the uniform buffer memory, right? So this is the actual copying. Um, while this guy, is linking, telling the shader which buffer it should read from. Okay, so it's saying let's read from binding 2 in the buffer, offsets, all of that good stuff, right? um, so this is right. So this is basically for descriptor set binding 2, use this buffer object with this offset and range. Okay, whereas the mem copy, whereas mem copy is actually transferring data um, into uniform buffer memory. Okay. And then in the shader, which is GPU side, remember this is a shader, GPU side, guys, GPU side. So we have our C++ CPU side, .cpp, C++ CPU side, all that good stuff. And then we have particle.comp, which is a shader, GLSL shader on the GPU side. Okay. So it's two different things that being at play here. We have to actually copy the data, but then we also have to tell we also have to tell the data which buffer to use, what offset range, all that good stuff, and what variables are we basically, you know, what variables are we assigning the data to so that we could do our processing here, attraction, repulsion, all of that good stuff. Not going to get into this in this video, in this algorithm, but I just wanted to go over all of that stuff as it relates to mouse state and things of that nature. While we're on the topic, do I want to? Do I did this in the previous handle mouse move, right? So this is sort of I'll get into this, but mouse state. Okay, so we have a structure here for processing the mouse information going on the basically connecting the operating system to the mouse and all that good stuff. And you know with that we have our handle mouse move X and Y, and that's what in our application, that's what allows us to basically have the application be able to know what's going on with the mouse from the operating system, location of the mouse, all that good stuff, right? And you could see when it leaves, it just leaves and then it comes back, all of that good stuff, right? So this is operating system side. Um, and we have our mouse state, which is just a struct that deals with all of that. GLM, the GLM inclusion gives us a position. I think GLM is here, right? GLM. GLM. Well, GLM, right? GLM, right? The GLM include is here, which is a library that helps us to connect all the dots. Okay. Um, but that's on the mouse handling side. But again, prepare compute. I'm sorry that I'm jumping around with the find feature, but it's really the only way to sort of get get things going. I don't know if you guys can see this because you guys are probably watching this on your phone and stuff, but we're at line 275, and this is the prepare compute function, uh, and we're the source code for this .cpp file is 586 lines of code. Okay, we are at 275, which is dealing with the prepare compute stuff, and then create a compute capable device queue. Um, we talked about queue families and all that. Create compute pipeline. Compute pipelines are created separate from graphics pipelines, even if they use the same queue family index. We need the previous particle position to calculate data for the current frame. So that's sort of what all this is dealing with. And of course, this is where we connect, as I showed earlier in the video. I'm 14 minutes into this video. I'm mad. This is where we connect. We basically from the CPU side, from the source code, we organize the buffer and everything so that the shader can read the buffer object and know the layout of the buffer and basically, get the x and y values from the for the mouse, and then that is what helps us to be able to calculate attraction and repulsion. Okay, and I'm done with this. I'm done with this example. I'm done with this example, guys. The next example that I want to do is the compute ray tracing, right? So compute ray tracing is basically we are doing ray tracing. We are doing ray tracing computationally. So we're not using the ray tracing extension. We're basically doing it, and I'm doing it on my integrated graphics card, not even the NVIDIA graphics card, but you could see that it's struggling because it's not the NVIDIA graphics card that I'm using. But I am eager to get to this example because a lot of stuff is going on, and yeah, I'm sort of done with compute particles. So anyway, guys, this is the last video in this series. Dive into it, guys. Dive into it. A lot is going on. We have our shaders here. We have three shaders: a vertex, fragment, and a compute shader. And then we have the source code here. Okay. So if you guys want to be able to run this stuff on your machine, um, make sure you get tutorial number 1, which installs the Vulkan SDK on your machine, and then tutorial number 13, which installs the examples, all the examples that we're running, um, all of these examples. Now, if you want to run the ray tracing examples, right, you need to make sure you have a ray tracing capable GPU. So it not only has to be a Vulkan capable GPU, but you need a ray tracing capable GPU. If your GPU is not ray tracing, you will still be able to run the compute ray tracing example because it's not using ray tracing hardware on your GPU in order to run it. It's basically just using regular GPU hardware, right? It's computationally doing it. It's not doing it using ray tracing hardware. So you will still be able to run this example, but you won't be able to run all of these examples down here. So if you're serious about learning computer graphics and learning Vulkan, you know, hang out with CUDA Education and I will show you the way. I'm learning it myself and I take you along for the journey. All right, guys, thank you for watching this video. You know what to do on the YouTube stuff. Support the channel, support the community, all of that good stuff. Have a great day.